to welcome today Stephen Mell from the University of Pennsylvania with linear logic as a language for structured data.
Yeah, thanks for having me. I admit this crowd is like probably 4 times bigger than I expected. And given how like sort of preliminary and even speculative this is, please forgive me. Also, there's I think a bit of a split audience here where I was warned that most people did not have like a background in like programming languages. And so for the people that do, this may be a little bit boring, and I apologize. I do not have this. It's right here. Hopefully people could hear me okay. Is this okay? Okay. So with that, this is based on some work I've done with my advisors, Osbert and Steve, although any foolish or incorrect things I say are mine alone. And also, please feel free to stop me at any time if you have any questions or clarifications or just objections. All right. With that, I guess, I want to ask if anyone in the room has done web development. OK, so maybe like half. Right, there are some structures that are pretty foundational when you're doing web development. So one of them is HTML. Have you seen something like this? HTML is sort of like a tree where you have tags that sort of form a tree. And you have things like links. And in this case, like links could be external, or they could also be internal. They can point to other parts of the page. So this is like the backbone of all the web pages you see. Another thing is servers. I guess I don't need to tell people in this room, but servers have databases almost always. And so for instance, like maybe you have something like Twitter or Mastodon. So you have maybe a table of people that have names, and then you have a table of sort of the following relation, who is following whom. So another pretty basic structure. And finally, anytime you talk between the client and the server, you use a protocol called HTTP, where you like send, oh, I want /Fibonacci from example.com, and example.com sends back like, OK. And then it sends back a sequence that could possibly go on forever of headers, followed by a sequence that could possibly go on forever of like bytes, basically. So in this case, like you can imagine, it's actually going to just send the Fibonacci sequence to you forever and never stop. And so I think a sort of implicit assumption that a lot of people in programming languages have, that I certainly like believe, is that programming languages should make illegal states unrepresentable. I think Ron Minsky at Jane Street was the one who coined this exact phrase that I like. And I think something I claim is that most programming languages that we use, at least in the mainstream, do not support any of these 3 structures very well that I have just mentioned. Does that, I don't know, is that plausible to people who have web development expertise?
You mean more precisely by support these 3 structures, like make illegal states, or make all legal states representable and all illegal states not representable?
I suppose I actually was just going to say more about that, so I think I asked for questions a little too soon. So for instance, right, if we have HTML, this is well formed. In particular, we have like a table of contents here with a link to section 42. This is sort of an internal link in that it points to the element in the page with ID section 42. And this is well formed because section 42 actually exists. But this document would not be well formed because this link actually points to section 24, which is not an element in the page. Or alternatively, this would also not be well formed because you could have 2 elements with the same ID. Right. And so, like for instance, you could represent this in like OCaml or Haskell with an inductive data type. But those data types don't usually let you express the constraints that you need. Or for instance, if you have a database, you sort of have a similar thing going on where typically tables have what's called a primary key. So in the people table, this ID, it's an integer, but it's not really an integer. It's not really semantically well defined to like add it or subtract it or something. It's really just meant to be unique. And then in the following table, you have a foreign key constraint, where you're sort of saying that all the entries in the following table have to point to IDs that actually exist in the people table. There's another thing about databases, which is here they're presented sort of serially, but there's actually no guarantee that if you give the same query to the database, you'll get the items back in the same order. Like formally, these are sort of multi-sets of rows, or I'll call them bags going forward. And then finally, with HTTP, I think Harrison probably has a lot of thoughts on this kind of stuff, but most programming languages don't really support infinite data structures very well. Like if you want to call HTTP a data structure, which I guess I would like to, And I think this is really important. And so the three things I'm pulling out of this, which obviously there are a million things you could want, but that I want that these are lacking, is first of all, the support for identifiers and references. So HTML exhibits this with these internal links. Database primary and foreign key constraints support this. And if you're familiar with like the problem of variable binding and representing syntax trees for compilers, this is also important there. And in most programming languages like OCaml, it's hard to enforce, I don't want to say impossible, but it's hard to enforce sort of the existence and uniqueness of identifiers. So another thing is sort of lack of order, and this comes up, say, in databases, but also in graphs, in multisets more generally. And here you could represent, say, a graph as like a list of nodes with some particular order. But now you sort of really, you care about equivalence classes up to permutation. And now if you want to write well-defined functions, you sort of need to know that those functions are permutation invariant over the input list. And again, like maybe you can enforce this in Calc, but in most programming languages, this is very difficult to do. Yeah, is that a, OK, no hand. And finally, sort of infinite data structures like streams, search trees are something that I've been dealing with a lot, where I would really like support in a programming language for dealing with them, or something like automata. So I guess I have like three sort of bold claims, which may or may not pan out. But first of all is that second-order multiplicative exponential linear logic can express all three of the structures that I presented here. And I mean, in some sense, the polymorphic lambda calculus, or system F, can already do much of this. And I think linearity is sort of important to me, but in some sense gives like a small boost on top of that. You can view linear logic as sort of a language of graphs and graph substitutions, and that makes this perspective a lot more intuitive. In particular, rather than thinking about intuitionistic linear logic, you can think about classical linear logic. If that doesn't mean anything to you, that's fine. You can sort of think about the proof nets or string diagrams for that language. I have like a sort of separate paper on an actual formalism for that I'm not really going to focus on here. And finally, I guess I think that we should actually use these things in our real-world programming language. And in particular, like sure, OCaml and Haskell have polymorphism, but they don't have as expressive a form of polymorphism as system F has, which I think ends up being really important. Of course, it's really hard to validate this without just writing programs. So actually, after Topos, on my break before I go back to Penn, my plan is to actually just like crank out an implementation of this linear system F. But we'll see how that goes. So these are my conjectures. I'm going to try and defend them, but I'm probably not going to do the most satisfactory job in the next hour. Yeah?
Are some examples going to come as we go for those of us who aren't that
yes.
on what exactly you're doing at Haskell and OCaml of like, here's a thing that I probably can't write right now that you think you can?
Yeah. So basically what I'm going to do is I'm going to give some high-level stuff for the programming languages people in the room so that they don't get too mad at me. And then I'm going to have like examples basically the rest of the time. So for PL people, I guess basically what I'm talking about is doing church encodings in something like system F. You can already easily church encode tree-structured data, inductive data types. This is a very standard thing that people have been doing for many, many decades. Infinite or co-inductive structures, I think also you can pretty much already just do with existential types, which I think is like an underappreciated fact, but also not novel at all. I do think that doing it in a linear world gets you a slight boost. You can do things like ensure that your streams get closed, but it's not that big of a deal. Similarly, identifiers and references, there's work on what's called parametric higher-order abstract syntax. And essentially, that's what I'm arguing for here. But I think there's a key difference where parametric higher-order abstract syntax sort of ordinarily variables are stuck under their binder. Like if you have lambda x, you can't reference the x outside. But when you're doing HTML, you actually want this. Like when you're doing HTML, you need to be able to reference the identifiers anywhere. And this is something which I don't want to say you can't do it without linear system F, but I haven't been able to figure out how to. And I have an example on an extra slide if you're interested at the end of actually doing this. You look worried, David. And then finally, for the rest of the talk, I'm actually just going to talk about lack of order and how you do that. Any PL heckling yet?
What's a closed stream?
I guess what I'm thinking about is you can imagine like HTTP comes in two phases. Like first you send a sequence of headers, and then you send a sequence of bytes. And if you were, I believe that if you were to do this in just system F, the inhabitants of the type corresponding to it, they could just like drop in the middle. They could send some headers and then just give up and never sort of send a close operation. Or it would be like if you had a file descriptor and you never called close on it or something.
But strings are infinite, so they usually don't get closed, or they don't just confuse. It's at the end, just so that
Yeah, I mean, I have an extra slide with a thing on it, so at the end I'd love to talk about it. Okay, and then basically my solution for the lack of order for PL people is to write something like this, where for a database, the database that I gave as an example, you write it as a function that takes two functions as an argument, one called person from string to x, and one called follows that takes an x and returns nothing. And basically I'm saying, when you want to create an Alice row in your table, you just call person with Alice and you get a reference back. And then you can call follows with the relevant people. And that if you, in addition to your usual alpha renaming as an equivalence relation on these terms, quotient out by reordering of independent lot bindings, then sort of the beta normal inhabitants of this type should be exactly directed multigraphs whose nodes are labeled with strings.
The error there is a linear function?
It will be. I'm going to work this out in more detail. And that this representation is sound in that functions that you write that accept this type can't impose an order on the underlying entries. And so like you think this is like for instance a bag. There's no way of pulling a single element out of the bag. But the representation is definitely not complete. There are definitely functions you can't write that you might want to write. Yeah, Owen.
It seems like the only way that you can get data out of this is via side effects.
I have a whole backup slide on this.
Okay.
Yeah, I would love to talk about that too. I'm glad you're skeptical though. Sorry?
You've been citing too much heckling.
No, this is perfect.
Slides for all the headlines.
And then you definitely can't do all of them, but you might be able to write somehow all monotone functions, like those that you can kind of compute in parallel. If you think about a database, it actually might be sharded across multiple instances. So there's some things you can't compute over all the data at once. But something I have written is the function that computes the followers of the followers. So there are at least some non-trivial things you can do here. But I'm going to get into more details, so unless there's more PL heckling. OK, great. So for the rest of the talk, I'm actually going to tell you how to do programming in linear logic. Then I'm going to show you basically the examples of doing lists, multisets, and databases. That's going to be the rest of it. How much time do I have? Great. 45 minutes? I'll try and leave time at the end for questions, too. So linear logic, I hope you've seen functional programming, because otherwise this isn't going to make any sense at all. It's essentially functional programming where you have to use all your variables exactly once. So for instance, this is a type. So let's take a moment to step through it. This type is functions that take an x, a function of x, and they return a pair of x's. So for instance, this would be an inhabitant of this type. I'm going to call the first x a, the second x b, and the function f. I'm going to call f with a and call the result c. And then I'm going to return c and b as a pair. Does anyone have any questions on this slide? Because if this doesn't make sense, none of the rest of the things I say are going to make any sense.
There's no particular reason not to just return f of a comma b, right?
Yeah, correct. I'm just sort of splitting it out to make it, yeah. Yeah, David?
It looks like you're applying these arrows to elements. I guess you can do that.
What do you-
These arrows really are arrows. They map to the category of sets. Sorry.
I'll return my functions to terms of the type. Right. There's nothing set.
Do I have to only use the function ones too? Or
Yes, you do. You do. Right. So one question that somebody probably should have asked is why I'm writing this lollipop symbol instead of a regular thing. And that's just because that's how you usually write linear functions in linear logic or something like that. But you should just think of these as regular function types.
The lollipop adds
I mean, categorically, I couldn't tell you exactly what it is. I think Valeria could. It's something like a symmetric monoidal, like closed monoidal category with some like comonad structure or something like that, which I haven't talked about yet, the comonad structure. But questions?
No, I'm just coming at this from a much more type theory side.
Oh, I'm with you. I'm totally
The
with you.
questions on the like, what is this in category theory for me are like exactly the reverse.
Yes.
One of the original motivations for linear logic was management of resources,
Yes.
but I haven't heard that in your discussion so far. Where you pinpoint any manipulation of resources, I haven't seen that yet.
Yeah, I suppose that's not the way I'm formulating it at the moment. Although one thing, like for instance, where I think if you're dealing with streams, it is good. Sorry, David. Is like it's management of the resource in the sense that like you have to close your stream when you're done, a bit like a file descriptor or something. So there's a flavor of it there. Yeah, I don't know if that's very satisfactory though.
So what is the resource in that example? The stream, the contents of the stream?
Yeah, sort of the state of the stream. Yeah. But. Okay. So then I might claim that this is another inhabitant of this type. Do people agree? Is this an inhabitant? Yes or no? Chris says no. Why is that? I didn't use F. Arg. So that's illegal. How about this one?
No.
I used F twice. Oh, curses. What about this one?
No. You can't calculate C and then get A back.
Right. There are two things wrong with it. One is that I didn't use C, and the other is that I used A twice. So just not really that interesting. But in fact, if this were all I could do with my programming language, I actually really provably couldn't do anything at all. So instead, there is what Girard called an exponential, which is not the same as the exponentials in category theory. So be warned. Sorry, Evan. And this is depicted with this exclamation mark or the bang. So this is takes an x, and takes a exponential of an x arrow x. And what this exponential represents is sort of an arbitrarily large supply of things. So it's like, it's not a function from x to x, it's a thing that will produce functions from x to x on demand. If that makes sense. Yes, Ellen?
Is it kind of like a Taylor series?
It is. It's very exciting. You can give some like denotational semantics in terms of vector spaces, where this is exactly what you do for like the exponential. The exponential is basically like the infinite sum of, yeah.
You have, but in multiplicative you don't have sums, but you just add this. Is that right?
Yeah, or correct. You don't have sums right now.
Okay, but you do have this kind of sum.
Yeah. Well, yeah. There's some sense in which like maybe it's like hiding a sum inside of it. Yeah.
It's producing an infinite number. Are they all the same, or they change when I draw one? Do I get a new one the next time?
You can give probabilistic semantics for this, in which every time you make a new one, you're actually sampling from a distribution. But for these purposes, think of them as the same. I love this stuff, but there are like a few like French logicians who do it, and so no one seems to know about it. It's not very accessible. Okay, great. So f is now not a function, it's an exponential. In particular, the way you use an exponential is you do exclamation mark. So this is a valid term because bang f is a function from x to x. And so it sort of all works out. And you can draw kind of like a proof-net string diagram-y thing on the right, which is a little imprecise, could be made precise. That's not important. Where, I guess, think about it something like this. So does this kind of make sense? Yeah.
It would have been a well-formed program without the bang, right?
Correct. Correct. Yes.
And when you say bang f is a function, you now mean that bang f is an x lollipop x without the bang.
Yes, exactly. Which means that I have to call bang f exactly once. Like, if that makes sense. Yeah. Are you worried, Chris? That's just kind of the rules of the game, I guess.
You can call f as many times as you want.
You can instantiate f as many times as you want. So for instance, this term that was previously legal is actually fine now, because when I say as many times as you want, that includes 0 times. So that would just be kind of like pass A and B through as the outputs. Or you could do something like this, where you do bang f of A. That would be. Does that all seem good? But is this one legal? No. Why is it not legal? Because it's the same reasons before. Like the bang f hasn't changed anything. C is still linear and was not used, and A is still linear and was used twice. So, okay. People following? Okay. Great.
Is the attempt to draw a diagram for that? Is there a reason to understand diagrammatically like that?
Yeah, because basically the rule for these wires is that they are a bijection between sort of filled and hollow ports or something like that.
This one's equivalent to a legal thing because he threw C away and used A and B exactly once.
Oh, like I could just erase this line?
Yeah, so it's not up to equivalence.
Or what do you mean?
Like this program, if you think of it as input to output, is a valid program.
Yeah.
Okay.
Maybe there's like some way you could repair it.
Okay.
But like under the rules of the game, this piece of syntax is ill-formed.
Okay.
If that's
But for instance, F could mutate A like B. I did not know that.
yeah. Or I mean, depending on what semantics you give it, but you might want to be able to give semantics that like support some kind of mutation under the hood.
Would an example be to use f on A and f on B to using f twice?
Yes, exactly. Which I have up here next.
Oh, sorry.
No. Right, so I've shown you how to use bangs, but I haven't shown you how to construct them. So this is what I'm going to show you next. So it's the same type. So suppose we have like this basic skeleton, we call the inputs A, B, and F. But now I'm going to like define G, where G is, sorry, this is really hard to read. G is like a let binding. It's a definition of something that is an exponential. And each instance of G will be a function from x to x to x times x. So for instance, one valid inhabitant of this would be, as Dana pointed out, instantiating f once for x and once for y. That makes sense. And then now G is itself an exponential, so I could instantiate G. I could pass A and B to it to get some C and D. Then I could instantiate it again and pass C and D to it to get I and J. And I could finally return I and J. Does that make sense? Yes.
How did your syntax know that G was going to be exponential?
Oh, because the type annotation right here.
And they knew that that was legal because you banged on both coordinates or something?
I guess the way I would think about this if I were implementing it is I would say, okay, I think I forgot to say something, but like I would annotate it as being an exponential, and then, well, I guess now I just have to provide a valid term on the inside. The actual introduction form for the exponential I've depicted with braces, which is not really a standard notation, but the braces roughly correspond to some kind of like internal box. Maybe ask your question again in a second. Like one thing to note here is this would actually not be a well-formed term, because a rule I haven't told you is only resources, or only things that aren't really resources that have exponential type can pass into a constructor. So this would not be legal, because B is a linear resource, and I'm trying to pass it into into a box, and that's kind of against the rules. So I don't know if that answered your question in any way. So the rule is like you can use things from the context as long as they also are of exponential type. You look worried, Kevin.
Yeah, interesting. Right. So if you tried that illegal definition and you wrote bang B a bunch of times, then that would involve using B a bunch of times.
Yeah, exactly. Right.
Can you define a let binding that isn't exponential that can be used only once?
In typical linear logic, you could. In some ways, that's not very interesting because, like, when you evaluate the let binding, you're just kind of rewire things. But you could, and typically people do. Yeah. It's called cut elimination in logic. So, sort of in that vein, you need to be able to compute with this, and the entire way you're going to compute is you're going to sort of say, like, well, G G, I sort of know the definition of G, and the way I would step this is I would like substitute the contents of this definition for every occurrence of G. And so this is the same term you saw before. So again, the same thing. I'm just like blowing it up a little bit to make room. So right, we define G to be bang f of x and bang f of y. We call G twice. And the way this would step as a term, the way it would evaluate, would sort of say like, okay, G, we're going to copy the definition of G in here. And yeah, you might have some like, Chris, like linear bindings. We might say like, oh, like in this occurrence of G, like G0, x was assigned to A and y was assigned to B. And then the output of that was, well, bang f of x, bang f of y, except we kind of have to do some like renaming. So it's bang f of G0 of x and bang f of G0 of y. But then we can kind of clean all that up, and we basically just end up with this. And then we can do the same thing with the second occurrence of G and get this. And now we have a let binding that's not, or an exponential that's not being used. So we could erase that. And like, I don't know, I think sort of what you'd expect. The term on the top would step to the term on the bottom. In particular, the term on the bottom would be sort of stuck. It couldn't evaluate anymore. Does that make sense? Sorry for boring you, Harrison. OK, one last thing, which maybe was too much detail to get into, but it's kind of important, is polymorphism, which you might be familiar with, like from Java or like whatever your favorite programming language is. JavaScript, I'm sorry. Right. So I don't know. If you're familiar with like polymorphism, well, like, sorry. This is a type which first it's a function that takes a type, which is what the star is about. It's going to call that type x. And it takes an inhabitant of x, and it returns an inhabitant of x. This is the polymorphic identity function, or the type of the polymorphic identity. And so the inhabitant of this would be, for instance, this just returns, yes?
Concern. You use lolly to take in a type, or does it mean to use a type 1?
It's like an exponential, where you can have like, you can take in an exponential, and you can still use it multiple times. Also, don't get too caught up on that. If you prefer, think of it as for all x lolly x. I just hated using Unicode in the middle of everything.
It seems like it's a different notion of quantification, though, right? Like typically you have to use your input once, and x is like very much not like that.
Well, but I mean, if you have a function and it's like bang f, or like bang x lolly x, it's like, it's fine.
Yeah, okay.
So like, for instance, you can also, so you can have functions that take types, but you can also have functions that return types. So here it's like, okay, foo is a type of functions that take a type x, an inhabitant of x, and they return a new type y, an inhabitant of y. This is like maybe getting off of where people are like comfortable with. But for instance, you could imagine this, where it actually just returns the type x as a type y, and returns little x as the inhabitant of y. Or like somewhat more interestingly, if I took a type x and a factory for producing x's, and I have to return a type y and an inhabitant of y, there are many things I could do now. But one of them would be to make y be x times x. So now I need to return a pair of two x's, which I can get by instantiating x twice. No one too worried? Cool. All right. Well, then with that, I guess this is polymorphic multiplicative linear logic, roughly, how you can write programs in it. I think it's pretty cool. But I guess now I'm going to try and justify that to you. Yeah.
So this x here is like times? And this
Yeah, sorry.
is that a variable?
Yeah, I'm sorry. That was really bad.
Okay, I just want to clarify that.
Yes.
Yeah, I thought it occurred twice. I was like, hold on, but okay.
Yes, Dana.
Do you have an operating system that will reject bad programs?
I have no implementation yet.
Okay.
But hopefully in
Don't
August,
ask
I will
me
write
that.
one. I actually have like about 7 failed attempts at writing an interpreter for this language. But they were before I'd figured out some of the details, so yeah.
Is this interpretation of exists y as a type of a type in terms of that type, like, consistent with what people normally call
Yeah.
effective?
Yes. Exactly. Well, and that's actually really, to answer Harrison's question about why I didn't use for all and exists, I think for all and exists from like a computational perspective give horrible intuition. And like really, I just think about for all is like a function that takes a type as an argument. And exists is just a regular pair where the first element happens to be a type.
That is much easier for me to understand.
It's like almost like dependent types, but like you don't actually need dependency to think about it that way. Yeah. Okay. Great. Any other questions on language? Because now I'm just going to use it. Oh, and you look a little upset. Okay. Okay. So I promised that we could represent data structures in this language. And I've even got time left. Wonderful. So I'm going to show you how to represent lists, which are a very basic data structure that people use all the time. And okay, it's this type, but let's actually step through it. A list is a function which takes a type, which I'm going to call like adjacent. And well, it takes something called nil, which is of this adjacent type. It takes something called cons, which is a factory for producing functions that take a t, in this case, a natural number, an adjacent node, which is the previous node, an adjacent node, which is the next node. So for instance, one inhabitant of this type would be I instantiate cons, I call it with 7 and nil. I call cons again, I pass 8 and whatever I got from before. I call cons again, I pass 9 and whatever I got before. Then finally, I return that result. Yes, Harrison.
Why is the nil thing not underlined?
It could be, but it doesn't have to be, unless you think this is an ill-formed
No, I think
program.
that was just happening.
I think I prefer this presentation because it's more symmetric. And reversing the list is actually trivial, but yeah. Yes, Owen.
Wait. Maybe I either have the same question as Harrison's, but I guess that just means I misunderstood Harrison's. The nil are, so you can use cons as many times as you want, but you can only use nil once.
Yeah, exactly.
Okay. Is that on purpose? Like, what would happen if you could use nil multiple times?
Sort of nothing. It would be a little bit maybe more like non-trivial to show, but basically you can imagine you had bang adjacent instead of just adjacent, which means you'd have a factory that you could use to produce nodes with one port, basically. But you could sort of show that you'd have to use that exactly once anyway. Just sort of combinatorially, like you could prove it. Yeah.
I don't know what list of t's usually. Sorry. Okay. I see.
Like, and I'm pretty sure you could like sort of write an isomorphism between these two types. Yeah.
I can use numbers as many times as I want.
Yeah, so I did like some sleight of hand here, and like, yes, I'm just assuming numbers are nonlinear. You could, for instance, define numbers to be a type that starts with an exclamation mark. Yeah.
Okay, I think I understand my question.
Yeah.
Usually in a list of t, you don't need to define a separate type. You just have the type.
You just have
List
it.
of t.
Yeah.
But here you have to define add as a type before you started.
Or
Why?
so like this is in some sense just the church encoding. So it's like it's a type argument. So like this is the type for all x, x arrow, t arrow, x arrow, x arrow, x. Does that make sense? So edge isn't like a new type.
Is a functor that takes a type and returns list. Returns an add type or takes it to add type and returns.
So
And returns this.
quantifying over edge.
Yeah.
It's the universal property of the inductive type. This is the add is the underlying set of the F algebra, of the one-plus algebra that you're going into.
What Harrison said.
This is add is not functor.
There's definitely some like mechanical translation between like some functorial presentation and like this quantifier approach. think that Harrison showed me like a couple weeks ago, but yeah.
So in a less galaxy brain way, if I were trying to write these programming language, would I ever plug something in for add?
Yes, which we're going to do right now. In particular, you might want to sum the numbers in this list. If, I don't know, that's a thing people do, right? So I'm going to write a sum function. Yeah, OK, sorry, I didn't mess this up. So sum takes a list of natural numbers and returns a natural number. And the way to think about these church encodings is that you sort of interpret every node in your object, like your list, with some computation, some like graph, basically, because this graph substitution thing that we were doing. And here, with sum, what we're going to do is we're going to interpret every edge as like where a number flows. So we're going to interpret adjacency with a natural number. We're going to interpret nil with 0. And we're going to interpret cons nodes with addition. And then, I mean, formally, like, I didn't have to like give these all names, but I think it's clear to do that. And then we just like pass them all to input. And what this would look like is here we're going to replace every cons node in our original list with this subgraph. And so if you were to do that substitution 3 times, you get this. Which now, presumably, you have some semantics for addition, so you can just chug along and everything's good. But this is sort of the mantra, is like when you're using one of these church encodings, you choose how you're going to interpret every node in the structure. And this is actually like pretty unintuitive for most people who've done functional programming, but you can give some. It has been proven that you can express any function this way that is provably terminating in second-order arithmetic, including Ackermann. So it's very powerful, but it's not actually Turing complete. But that's maybe beyond the scope of things. So does this sort of make sense? So now we might want to, instead of like summing a list, we might want to transform a list into a list. So here, I'm going to write the identity function, which is not going to be the most interesting. If I write the identity function, sort of, well, the identity function takes a list of natural numbers and returns a list of natural numbers. And so a list of natural numbers is itself a function that takes adj, nil, and cons. So really, this type is a function that takes 4 arguments: the input, the adj type, nil, and cons. I'm going to interpret the edges in my original list with edges in my new list. I'm going to interpret nil with nil. And for every cons node, I'm going to replace with a single cons node. So if you sort of did the substitution, you'd get the exact same thing back out. Yeah?
So in church encoding, all the functions in there have to end in adj.
All the.
You have adj, you have t to adj to adj, and you have add at the end.
Wait, sorry, could you ask the question one more time?
On list t, like,
Oh.
there are rules for how that can be constructed, and they have to all end in adj.
So if you were church encoding an ordinary inductive data type, yes. The whole point of my bag encoding is that it won't do that. We will not do that.
You don't have to do that.
Yeah. But I'll get to that in a second. So then a slightly more interesting thing is you might want to write a stutter function, which sort of replaces every node, like cons node, with 2 cons nodes. So it sort of doubles the length of the list by like duplicating each element. So the way I'm going to do this is I'm going to interpret. So I'm going to interpret cons with, well, first instantiate a cons node, then instantiate another cons node. Get kind of wired together like that. Does that make sense? This is about as complicated as things are. Actually, that was a lie. This is the second most complicated that things are going to get, but I don't want to lose anyone too badly. And basically, this would evaluate to this list, which would be twice as long. Okay. Then it's not the most important, so I'm going to kind of breeze this next one. You can do even more non-trivial things, like, for instance, computing the Cartesian product of 2 lists. So I'm going to make a second list, which the first list is 7, 8, 9. The second one is true, false. You can compute the Cartesian product by first, well, it takes a list. It's going to, for technical reasons that will become clear in a second, take an exponential of a list. It's going to return a list of nats and bools. And so, well, as before, we're going to interpret every node in our A list with something. And what is that going to be? It's going to be, well, we're going to instantiate B. We're going to make a copy of B, so the true-false one. And then, oh, OK, but once we instantiate B, we then have to interpret it as well. And we're going to interpret every cons node in the copy of B with a cons node in the output list. And so, well, if we just consider this block here, we have a copy of B. We're interpreting that. So if we do the inlining, we're sort of going to end up with this. I'm probably losing people here, and that's probably OK. So it's sort of going to be some value A that is brought from one of those, and cons true, cons false. And then finally, you're going to inline it all the way. And you're going to end up with 3 copies of this, 1 for each of the elements in there. Yeah.
Is it actually important that you can copy the list of rules, or could you just like copy the rules? Or if I can go from
Yeah.
the list of bang A to bang with list A.
Yeah, I think as long as you're with some conditions on the types inside the list, yeah, you can like turn a list into a bang list.
It's important here that that rule are copyable.
Yeah. OK. Great. All right. I guess I am sort of running out of time here. So I promised you, so this is actually completely standard. This is a church encoding of a list. I mean, I do think the graphical presentation is maybe somewhat novel, but like the underlying ideas are super old. However, I promised you bags. And how am I going to do that? Well, if we sort of squint at this list, 7, 8, 9, this won't necessarily make any sense to you, but it's like, what makes this a list instead of a bag? It's sort of that we have this like total order that's being imposed that we pass along. And well, why do we have that? It's because at every step we got something from the left, from the outside world. Every node we have to like pass that thing. So it's sort of like, what if we just delete this? What if we actually just got rid of everything except the t? So the type here is just t arrow nothing, bang of that arrow nothing. And like, what am I claiming the inhabitants would look like? So well, a bag of gnats is just a function that takes an add function, or add is what I'm calling this function, which takes a number. And well, you can call it some number of times. Does that at least formally make sense? It's like the type you could write, this is a valid inhabitant of that type. But, right. So I'm just like shortening it, getting rid of like the unit equals. I think this is a thing you can do. You might say, like, why would I want to do that? Well, because I think I haven't proven this, but I'm fairly confident that is true. I have like sort of a sketch. You can't write a function over this type that would assign a particular order to the elements. But so then the question is, can you still do interesting things? And I think the answer is yes, but I guess that's a little bit up in the air. So for instance, we can sort of play the same game. We can write the identity function. And now how do we use a bag? Well, we interpret the add nodes in it. And in the identity, we'd interpret the old add nodes with new add nodes, which would be sort of like this. Wouldn't be that interesting. But we could write, say, like the double function, where here we're interpreting an add node with a pair of add nodes with the exact same value. And so it would be like that. We'd do our substitution, something like that. Or we could do our Cartesian product example as before, sort of the bag analog of everything. So we have bags with 7, 8, 9, and true and false. And how do we compute the Cartesian product? Sort of the same way. We're going to interpret all the nodes in the A bag. What are we going to interpret them with? A copy of B. In each copy of B, we're going to interpret each node with an add. And I think from a functional programming perspective, this is very weird. But I think the way to think about it is almost like you're doing a for loop over all the elements of the bag, but you can't pass any information between iterations of the for loop. But what you can do is sort of almost imperatively or effectively call add and sort of add to it. Except at the end of the day, nothing effectful is happening at all. So it's sort of the same story where you end up with something like that. Now people seem worried.
So is the fact that your runs through the for loop can't talk to each other mean that you can't write sums?
Exactly.
I would like to be able to write.
You'd like to be able to write some. Well, boy, do I have a slide for you at the end. That we'll almost certainly not get to, but I'd love to talk about afterwards. Because I gave the talk on Friday and people had objections. Right. So then, okay, I guess time is okay. I'm going to go maybe, I think this is the crux of it, but like, how does this let you do databases? So like, here is the database from before. We have people and following. This is basically a directed multigraph where the nodes are annotated with strings.
You won't be able to print.
Print?
You'll be able to print it too?
Print it? No.
Yeah. You won't be able to print it.
No, because that would be like violating the
that's
invariant.
fine. Okay,
Yeah.
So you can't, this is not, okay.
Yeah, no, sorry. This is very intuitive. This is not.
In the computer, that can never be output.
Yeah, at least not without axiomatizing additional things,
Okay.
which I think you can do in a sound way. But so basically, that database schema, what I'm sort of claiming is it's this type. So now we have a type variable again called personRef. We have a function. So what is an instance of this database schema? It takes 3 arguments. One is the personRef type. One is a function I'm going to call person, and one is a function called follows. You can think of these functions as add a row to the relevant table. So you can call person once and pass it the string Alice. We can give this the identifier Alice, but I mean, sort of by alpha renaming, it's not really called Alice. It's just a unique identifier. Similarly, we do this for Bob and Carol. So we've got these identifiers, and now we can call follows, and we can pass these things to them. And so a term would look something like that. So now, I guess something I should say here that's kind of important is, so ordinarily your notion of equivalence on terms is alpha renaming of variables. In sort of proof nets or string diagrams, one of the ideas is to quotient out unneeded structure. And I think the right notion of unneeded structure to quotient out here is essentially reordering of independent let bindings, which is, I don't know if this is formally exactly true, but if you look at proof nets for linear logic, this is approximately what they do. Yes, David.
You could add Alice twice, or add Alice follows Bob twice.
Yes, yeah.
It's not a relation, it's a span.
Yeah, it's, yeah. But like, there are actually some weird implications of this. So like, I feel fairly confident that this means that like the normal terms of this type correspond in a very natural way to the directed multigraphs, where the nodes are annotated with strings. But it would also imply that checking the equality of 2 terms is now graph isomorphism complete. I actually think this is a good thing. It means you're quotienting out extra structure. And in particular, you don't need to check equality of terms to do things like reduction, or really most things, but it's like a bit weird. Right, and then, so just scrunching things up a little to make room. So I could, again, write the identity function. And how do I write the identity function? Well, I say how I'm going to interpret person nodes, and I say how I'm going to interpret follows nodes. I'm going to interpret person nodes with person nodes, and follows nodes with follow nodes. And you do the substitution, and you get the exact same thing back. But I could do something slightly more interesting, like I could try and symmetrize my graph. So how do I do that? Well, I interpret person nodes with person nodes, but I interpret follows nodes with, well, a follows node in the forward direction and a follows node in the backward direction. And then this would step to this. And I do not have a slide with it, but I have written in a markdown document sort of an implementation of like the following of following relation. So that's a somewhat non-trivial thing you can compute without actually needing to, like, I don't know, serialize, provide an order on the structure. So I guess this is basically what I had. So I'd be happy to take questions. I guess sort of these are my core claims, and I have some extra slides for, well, streams, parametric high-order abstract syntax in HTML, and some of these questions about like database ordering and how you do sum. So, yeah. Although, to be clear here, I'm pretty confident this works, but at the moment, it's no proofs, just vibes. Yes?
Could you explain why you can't do this nice visual proof-net thing in intuitionistic linear logic?
I don't want to say you can't. But I guess one of the things here, right here, is I said, oh, reordering of independent let bindings. So I guess that would sort of imply I couldn't move Alice below the follows involving Alice. If you do proof nets for classical linear logic, you actually just throw that out. You actually say there is no ordering whatsoever to any of these statements. It's just a bag of statements, and you have a certain like acyclicity condition on them. And I mean, I hesitate to say you can't do something for intuitionistic version, but like in some ways when you're thinking about it as a graph, it's very natural to just think of it as like some big soup of stuff. So I don't know if that's satisfactory, but.
I will ask him later.
Okay. I asked Frank at OPLSS last year whether he had something against classical logic per se, and he said no. I just haven't seen it like be useful. So this is my my attempt to make classical linear logic useful.
So what did I gain here with these linear type definitive lists and bags over a Cartesian line?
Over Cartesian?
Yeah, like is doing this linearly getting me much yet?
Right. So I don't want to claim you can only do it in linear logic. I think the reason that I like linear logic is the proof nets are how I think about things. And I mean, yeah, like those came from linear logic, are very natural there. The other thing is this actually doesn't work in just nonlinear lambda calculus. In fact, I think a lot of people with some exposure would think this is really weird because this is a function that just returns unit, and so they think it's just unit.
But the fact that Alice appears exactly once and Alice Bob is like two identifiers, person refs, and not like a bunch of Alices and then a bunch of Bobs, is using the linearity rule. In the bang follows Alice Bob, the fact that Alice and Bob, that pair is an ordered pair of one person ref each.
That's
not the linearity?
That's not, no. That one works like intuitionistically. I think there are examples, although I'm like struggling to come up with one off the top of my head where it's important. But like one of the key reasons why this wouldn't work in like the standard nonlinear setting is like, are you familiar with call by value and call by name? Like if you think about in Haskell, if you were to write this function, you'd sort of say, okay, I'm returning unit. Unit depends on none of these things, and so you just throw them away. And so now all these terms would just reduce to unit, and it would be pretty useless.
Yeah, I mean, there's only one function in the terminal object, and if you I guess you can have more.
And so I think if you were to do this in like a call by value setting, it would be kind of okay because operationally you'd get stuck. You'd say, oh, like I want to call person. I don't know what person is. Like I'm stuck. And so now you'd at least have distinct values. But now, like ordinarily, like if you think about system F, you don't specify an evaluation order, it's confluent. So it would evaluate a unit anyway. Whereas I think in linear logic, it doesn't degenerate in this way.
Can I follow up on
Yeah.
that? I think it seems like an important aspect of what's going on here is the ability to support effects. Because call by value and call by name are the same if you don't have effects. The
Yeah.
interesting thing is
Yeah.
when the follows function is doing some effects, which could
Yeah.
be what the lolly doing over arrow.
Yeah, and it's almost like you can sort of think of these effectfully, and there are no effects in the language per se, but it's almost like it supports the ability to add effects later in your semantics or something like that.
So do you have an idea of what like a denotational semantics for this would be? Like it's clearly not set in Cartesian Monroe category.
I mean, there are like in some sense like there are standard semantics for linear logic. Like there's one called coherent spaces. People have given denotational semantics in terms of vector spaces and relations. That gets like very infinitary very quickly though.
So you're thinking of it mainly operationally?
Sort of at the moment. I mean, I do have this sort of like almost like hobby interest in like these vector space semantics. Yeah, I guess also people have given like semantics in terms of like quantum programs because you can kind of think of proof nets as like quantum circuits or something like that. And so that comes up there as well. But in terms of standard semantics, I think the most standard semantics for linear logic is these things called coherence spaces, which they're some kind of domain with extra structure, if you will. So yeah, I guess not said. Yeah. Yeah.
Can I count the number of people in my database?
Yes. Sort of. Okay.
Can I count the number of people in my database in a way that isn't returning a bag of
Units. No.
Can I get something out of the bag of units?
Another bag?
Can I get a not bag thing out of a bag of units?
No, basically, I think not. Which,
Should be inside of a larger programming language.
right, exactly. And so for instance, something I think is actually kind of reasonable is like you can't write a function from like bag t to list t. And for instance, sort is basically of that type. So yeah, you'd have to axiomatize it. But something that's like kind of weird here that I don't really have any proofs for you, but like kind of feels right, is it's like not only, you don't kind of only do like monotone things on bags. And I think this comes up in databases a lot as well, where like your database might not be on one computer. It might be divided. And there are certain operations that are like a lot, there are certain operations you can kind of just do in parallel. For something, there's something called like CRDTs, like conflict-free replicated data types or something. And in many ways, these are kind of similar, where it's something where you want everybody to be able to just do computation in parallel and know you're going to get the same answer at the end. And like in those, there's something called like a PN counter, and it's how you represent an integer as just like ever-growing positive and negative components. And you interpret them as one subtract the other, but it makes it like coherent if you do it in parallel. So you could axiomatize the function that goes from that I would call like weight from monotone nats, which are just bags of units. So to have bags of units and lists of units. And this, like, in some sense, is like clearly a sound function to axiomatize, in that like bags of units are the number of times you call add, and lists of units are the number of times you do cons. But it's something you can't really do in parallel, because you'd sort of, if you were doing some giant database query, you'd need to like wait and know that the computation was done in order to convert it into like a regular nat. And if you're willing to axiomatize that, then sure, yeah, you can like sum your bag of nats into a nat. But yeah, I don't know whether that's satisfying. It's kind of weird. Yeah.